You may want to have a highlighter or a pencil or whatever handy. We spent considerable amount of time on
F equals ma.
considerable amount of time on Friday dealing with Newton's first law, and it sort of melds into the second law a little bit. So we're going to be looking into that as well today. Okay. There are no clickers. There are no clickers for this one. In fact, there is only really one question that you're going to encounter. Okay, but let me just sort of go through this with you. So, what's the big deal? Newton's second law, big misconception. What's the big deal? Many people have known Newton's first law since 8th grade or earlier, and have prompted with the first few words. Most people could probably recite the law word for word. And what is so terribly difficult about remembering that F equals ma? You've probably used it already in grade 9 and grade 10. It seems to be a simple algebraic statement for solving story problems. The big deal, however, is not the ability to recite the first law in order to use the second law to solve problems, but rather the ability to understand their meaning and to actually believe their implication. And you may say, I believe it, I get it, but then when I give you a situation that you're supposed to apply that knowledge, you fall back on sort of some pre-held misconceptions, and you don't demonstrate that you truly do believe it. So that's my job, is to get you to convert, if that's the case. Okay? So, while most people know what Newton's laws say, many people do not know what they mean, or simply do not believe what they mean, or cannot apply them, might be a better way to say that. Cognitive scientists, scientists who study how people learn, have shown that physics students come into physics class with a set of beliefs which they are unwilling or not easily willing to discard, despite evidence to the contrary. These beliefs about motion, known as misconceptions, hinder further learning. They don't allow you to sort of move further. The task of overcoming misconceptions involves becoming aware of the misconceptions, considering alternative conceptions or explanations, making a personal evaluation of the two competing ideas, and adopting a new conception that is more reasonable than the previously held misconception. What is that law called when you're supposed to pick the simplest law of parsimony, right? The law of parsimony says you should pick the simplest explanation. And as I said this morning, more often than not, I've found that the simplest explanation is actually more challenging for students, likely because of those misconceptions that they already have. Well, I give you a simple explanation, and kids just can't seem to think that it's, oh, that's so simple, and it's actually very hard for them to sort of make that adjustment. Kind of thing. So, again, part of my job. Self-reflection, critical thinking, and evaluation. While this process may seem terribly complicated, it's a matter of simply using your noodle, your brain, and actually believing it too, right? Believing it. And feeling that it's okay to throw away some of your ideas. Okay, so let's get into it here. The most common misconception is one which dates back for ages. It is the idea that sustaining motion requires a continual force. Okay, if you want to keep something moving, you have to keep pushing it. Everybody knows that, right? I'm pushing the desk across the floor, I got to keep pushing it. But that's not what Newton says. Exactly. The misconception has already been discussed in a previous lesson, the one we did Friday, but will now be discussed in more detail. This misconception sticks out its ugly head in a number of different ways and at a number of different times. As you read through the following discussion, give careful attention to your own belief system. View physics as a system of thinking about the world rather than the information that can be dumped into your brain without evaluating its consistency with your own belief system. So you have to actually think about the stuff that I'm talking about. Robert, you need one of these. Okay? And while I'm on this particular point, how many people, and you don't have to put up your hand, just sort of think, yeah, I'm in that camp. How many people have realized now that physics really isn't, there's not a lot of memorizing going on in here? Not a lot of memorizing, right? I'm not going to ask you for definitions, or there's a few of that kind of stuff, right? But for the most part, you have to apply new situations. You have to apply something that you've learned to that and apply your knowledge and think, right? And it's only going to get better or worse, however you want to look at it, right? More of that, okay? So be aware. Yes, and that's one reason why I allow that cheat sheet, right? Because I want you to have that database of knowledge there that you can look at and then apply to something new. Okay, so anyways, Newton's laws declare loudly that a net force, an unbalanced force, causes an acceleration. And that would be the first thing I would like you to highlight. Where is it? A net force causes an acceleration. Net forces cause accelerations. Okay? And the acceleration is in the same direction as the net force. Now, most of the time people get that. That's not too much of a big deal. It comes into a bit more play when you talk about circular motion. To test your own belief system, consider the following question and answer as seen by clicking a button. You can try as you want to click on your paper. It's not going to work. Okay. Are you infected with the misconception? I have the virus. I have the antidote. Two students are discussing their physics homework prior to class. They are discussing an object which is being acted upon by two individual forces, both in a vertical direction. Here's the picture right here. Okay, this is called a free body diagram for the particular object. Okay, this is called a free body diagram, and we're going to be looking at those in more detail later, and you're going to be drawing some of them. During the discussion, the student, analytical, thank you, suggests to another student, know a formula, that the object under discussion could be moving. In fact, Anna suggests that a friction and air resistance could be ignored because of their negligible size. What does the word negligible mean?
Neglectable.
What?
I don't know.
No, I just didn't hear you.
Neglectable.
Neglectable. Yeah, that's pretty close, actually. What does that mean, neglectable?
You can forget about it.
You can forget about it. Negligible means that it's so small, you don't have to worry about it. Okay? It's just not really a factor. The object could be moving in a horizontal direction. So Anna suggests that if friction and air resistance could be ignored because they're too small, the object could be moving in a horizontal direction. She says this object could be moving. Could be. According to Anna, an object experiencing forces as described at the right could be experiencing a horizontal motion as described below. Could be. Noah formula, he's a smart guy, he knows all his formulas. Objects, arguing that the object could not have any horizontal motion if there are only vertical forces acting upon it. He says it can't be moving sideways because there are only vertical forces. Noah claims that the object must be at rest, perhaps on a table or floor. After all, says Noah, an object experiencing a balance of forces will be at rest. Who do you agree with? Now, don't yell it out. I'm just going to write these down in here. Anna says it could be moving.
Which direction?
Left or right. Noah says it must be at rest. What I want you to do is I want you to write down on your paper who you agree with, and your neighbor is going to answer for you. So you must write something down. You must write something down and make sure your neighbor does it, and rat them out if they don't. What I want you to do is I want you to answer for your neighbor. Answer for your neighbor, okay? Hands up if your neighbor agrees with Anna. Could be moving. Hands up if your neighbor says could be moving. Hands up if your neighbor says it has to be at rest. Interesting, because the morning class was completely the opposite.
Law of parsimony.
And they're smarter than us.
How many people think their neighbor's wrong? I don't even know what to say. The correct answer is it could be moving. See, I told you. An object in motion stays in motion. Yeah?
It could have been moving prior to...
It could have been moving. We never said it wasn't moving. We just said it's just a picture, right?
The net force is zero.
The net force is zero, exactly. The net force is zero, which means the net force is zero, which means the acceleration is zero. But that doesn't mean it's at rest. It could be moving at a constant speed. You do not need a force. You don't need some big arrow like this showing that it's moving to the left.
So the law of parsimony doesn't work for that
Yeah,
one.
but Noah formula knows all these formulas.
Yeah, but analytical,
And again,
she analyzes things. She's right. Now, does it have to be moving?
no.
No, and that is the key there. It doesn't have to be moving. She says it could be moving, or it could be at rest too.
Oh.
No, he said it had to be at rest.
So the law of
He said it
parsimony
had to be at rest.
So physics is all about trick questions then?
Good point, Ben.
And law of proximity
Good
doesn't
point.
work.
It could be moving or it could be at rest, okay? You do not need a force to keep it moving. Now, you're going to see in the near future, I'm going to ask you a question about one with friction in it. So, similar kind of idea, and I'll explain that when I get there. Okay, so here's some explanation. Remember last winter when you went sledding down the hill and across the level surface at the local park, and this is from the internet, so they're apologizing for people that live in Mexico that have never been tobogganing. Imagine at the moment that there was no friction along the level surface from point B to point C, and that there was no air resistance to impede your motion. How far would your sled travel, and what would its motion be like? Most students will quickly answer the sled will travel forever at constant speed. Without friction or air resistance to slow it down, the sled would continue in motion with the same speed in the same direction. What's different about this picture here? Nothing, okay? There is no friction there. But because our everyday life revolves around everything having friction, we assume that friction is going to be present. We can't do that. Okay? We do try and reduce friction quite a bit. Okay, so the forces acting upon the sled from point B to point C would be the normal force, and more on that in the near future, and the gravity force. These forces are balanced, since the sled is already in motion at point B, it will continue in motion with the same speed and direction. So, as in the case of the sled, and as in the case of the object which Noah and Anna are discussing, an object can be moving to the right even if the only forces acting upon the object are vertical. Forces do not cause motion. Forces cause accelerations. And what are accelerations? Simplest explanation?
Changing the law.
Changes in motion. Okay? And that's one of those sort of simplistic things that makes it kind of hard to understand. Forces do not cause motion, forces cause accelerations, which are changes in motion. If you want something to change its motion, you have to put a force on it, right? If I want to push the table, if I want to get it moving, I have to push it, right? How come I have to keep pushing to keep it moving along the floor, though? Because of friction. It's the net force idea that you have to keep in mind, right? Okay, it's the net force idea. If there's friction, do I need to push? Yes, because I have to make the net force do it. And that's the difference. Is there anything else there? Is that the end of... Oh yeah, then there's some little bit at the end, isn't there? Yeah. Newton's first law of motion declares that a force is not needed to keep an object in motion. Slide a book across the table and watch it to slide to a rest position. A book in motion on the tabletop does not come to a rest position because of the absence of a force, but it is the presence of a force, being friction, of course, which brings the book to a rest. In the absence of a force of friction, the book would continue in motion with the same speed and direction forever, or at least to the end of the tabletop. A force is not required to keep a moving book in motion, and a force is not required to keep a moving sled in motion, and a force is not required to keep any horizontally moving object in motion. Done. All right, so we're now going to spend the rest of today's period talking about free body diagrams. To be able to do the word problems that are coming up in the very near future, you have to be able to draw the appropriate diagrams. So, free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting on an object in a given situation. A free body diagram is a special example of vector diagrams. These diagrams will be used throughout your study of physics. This is not the one that I'm reading. It's not the right one, is it?
No.
All right, now I got the right one. Free body diagrams, otherwise known as FBDs, are simplified representations in a problem of an object, the body, and the force vectors acting on it. This body is free because the diagram will show without its surroundings, i.e. the body is free of its environment. This eliminates unnecessary information which might be given in a problem. Let's take this figure to be a pictorial representation of a situation, a sled on snow, and there's a picture of it with the horse, with horses pulling it. First, we're going to represent the sled, the body in our problem, as a really simplified figure, a square resting on a flat surface. And we tend to draw free body diagrams just with boxes. Some books will just use a dot. Okay? Okay, so the first force that you would probably almost always have is gravity, right? The first force we'll investigate is that due to gravity, and we'll call it the gravitational force. We know that the acceleration due to gravity on Earth is approximately 9.8. And if you didn't know that, now you do. 9.8. The force by Newton's second law is Fg equals mg. Now what I like to call it is the weight force. So where does that formula come from? Well, it comes from F equals ma. A is our acceleration, but in this case it's the acceleration due to gravity. So what I like to call the gravitational force is the weight force. So I tend to write Fw is equal to mg, and you'll see it over here as well. Fw is equal to mg, mass times gravity. The g takes the place of the a, right? G is equal to 9.8. Okay? Where g is the acceleration of gravity and m is the mass of the carriage. Let's add this to our diagram. You can see it over there on the right-hand side. It's an arrow pointing down. Does gravity always point down?
Yeah.
Oh, straight down. Note that the force vector labeled Fg or Fw points downward, as this is the direction which gravitational force acts. This is also commonly called weight. This weight mg is different from where we get used to the word weight, which is known in physics as mass, right? When someone says, how much do you weigh, you tend to give them an answer, usually in pounds, which is the person's mass, not their weight, because your weight will actually change as you get farther away from the Earth. Ben has a question.
If you were to get stronger.
Ben's question is, if you're near the center of the Earth, will your gravity change? And yes, although because gravity is a mass thing, as you go down, 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 I have a handout for this in the next unit, then there becomes mass above you, which is actually attracting you up as well, right? So it.
So you could kind of be, so in the middle, are you just like in free?
Zero gravity.
No, that's awesome.
Now, you have to actually climb down a ladder and jump out though, right? Because if you jumped in, you're going to be actually moving.
But if you're just up here in the middle.
Right. We'll get to that.
Oh,
Oh yeah, so mass and weight, gravitational weight force is called your weight. Now, how many people are nerdy enough to have a bathroom scale at home that measures you in newtons? Anyone?
You?
Really, Aurora? You and me have something in common then, because I have a bathroom scale that measures your weight in newtons.
You shower curve periodically?
No, I do not have a shower here. In fact, I have it here. I don't have it at home. So what I want you to do is, I want you to see if you can guess my weight in newtons. I want you to guess my weight in newtons. Write down a number.
What's one newton equal?
I've given you the skills. Mass times gravity. I've given you the skills. I'm going to give you 30 seconds while I do my tenets. I want you to guess my, not saying.
How much is that in pounds?
Well, you figure it out. Weight force is mass times gravity. 750 newtons is my mass times gravity. So my mass is going to be 750 divided by 9.8. Someone help me out.
76.5. You're not.
76.5 kilograms. In pounds. Get out the phones.
Actually, how big is it?
Do you? Logan's going to tell us 76.5 kilos. Or you could just go times by 2.2. Okay.
That's usually 153.
I guarantee you, he's 183. You're 183, right?
168.
168? I think they weighed. I think they weighed me at the doctors are a couple of schools.
Exactly
167.
168. I knew he was.
So how much stone?
But 750 newtons is my weight. So yeah, when people ask me how much do I weigh, I say 750 newtons, then they look at me funny.
Can you see how much I weigh?
Go on. Well, actually, I'll give you a chance later. Okay. Okay. Let's move on. Now, the normal force, right? Anyone feeling a little normal today?
Yeah.
A little less than normal?
Yeah.
You're still giddy from the weekend?
Yeah.
Yeah. The normal force is the one that prevents objects from falling into whatever it is they're sitting upon. It is always perpendicular to the surface with which an object is in contact. Normal force is always perpendicular. What does perpendicular mean?
5%.
Opposite.
If you had to give a number, 90 degrees. 90 degrees. The symbol for perpendicular, anybody know? The upside down T thing? Right? Perpendicular, normal force. So, for example, if there's a crate on the floor, we say that the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force on the crate points upward, perpendicular to the floor. It's called the normal force because normal and perpendicular mean the same thing, apparently. The normal force is always perpendicular to the surface with which a body is in contact. For a body on a sloping surface like a ramp, like this one right here, the normal force is perpendicular to the slope. Okay? So please watch that. It's perpendicular in there. Right? And that's labeled Fn. Some books label it F with a perpendicular sign. Okay? Fn.
What? I don't understand what you mean.
Fn or F perpendicular.
F per.
So what
Okay.
happens to zero gravity?
What do you mean?
Like what's the surface down? Is there surface?
Where would there be zero gravity?
Space or something?
There's gravity in space. Yeah. We'll get to more gravity stuff later. Okay, let's talk about friction. Related to the normal force is the frictional force. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular to the surface, the frictional force is always parallel, same direction. Furthermore, friction opposes motion, so its vector always points away from the direction of movement. Friction is divided into two types, static and kinetic. Static means at rest, not moving. Kinetic means moving. These are represented by FF with a further subscript S for static friction and a subscript K for kinetic. As its name suggests, static friction occurs when the body is not moving with respect to the surface. It's the force that makes it difficult to start something moving. On the other hand, kinetic friction occurs when the body is sliding over the surface. Rolling objects experience friction as well. Rolling friction is actually very complicated, and we're just going to ignore it, or assume that it's sliding instead. This is the force that causes objects to slow down and eventually stop. Friction is usually approximated as being proportional to the normal force. The proportionality constant is called the coefficient of static or kinetic friction. Coefficient of friction. Now, you may have heard about my grade 12s. We measured the coefficient of friction between a pancake and a griddle. We got a number. It's 0.49. That's how much friction there is between pancakes and griddles. Okay?
Is that like a bonus question on this?
No. I'm just telling you just for fun.
Did you slide it down?
We slid it down a ramp and measured how fast it moved, and that's how we came up with it.
Good, that's all pancakes are worth using.
Oh, sorry to hear that, man. You hate pancakes? Really? The letter that we use for the coefficient of friction is the Greek letter M, which is a funny-looking U.
Didn't you say the friction changed though with the temperature?
Yeah, as the pancake cooled, the friction got less. And I have two theories. One is that, you know how when you take a lid off a hot pot and you put it down on the stove and then it cools and it creates that vacuum in there, right? That would be one thing I think, that when it sat there, it was warm and then it cooled and then there was air pressure holding it on. And the other one is that because it's moist and wet, that's created a bit of a seal, and so it wouldn't slide. So
would that be with like all objects?
that they would lower their friction when cooled? I don't know about that. That's a good question. I don't know.
Not ice.
The only way to figure it out, we could measure a block of wood and then take it outside and freeze it, and then we could try that, I guess. I don't know.
Well, what would happen with water and ice? When it's water cooled.
Yeah, that's a different state, though, right? So the letter that we use for coefficient of friction is the Greek letter mu, and you're going to see more of that certainly in grade 12, a little bit in grade 11. Mu. Okay, so I've added frictional force to this free body diagram right here. Okay, another chance for you to demonstrate your knowledge here. Is that object moving? Yes, it's moving. No, it must be at rest, or I'll accept a third one. It could be. Okay, how many people think this object must be moving?
Is that F, that's, oh, no.
Bo says yes. How many people think it? I'll give you another chance to change your vote once we go around the horn here. Must be moving? Must be at rest? Could be moving or could be at rest? Ben and Bo are right. This one must be moving. Do you want to explain why, Ben? There is clearly friction here, right? And if there's friction, does there have to be movement? No, there doesn't. Because I can push on the big filing cabinet and friction is there and it's not moving. So how come this friction means that that this has to be moving.
But if
What do you mean by that, Connor?
Like there's only one, like there's only pressure and force.
Force. There's only force one way. So what you're saying is there is a net force, which means there's an acceleration, which means it has to be moving, right? It has to be moving. In fact, this object here is actually slowing down, right? If I drew this in, if I drew an applied force in there like that, which is what we're going to see right away, and they were equal, then the answer is at rest or moving. But because there's only one, Connor's right, it's unbalanced, there's a net force, must be moving. Physics is nothing but trick questions, right, Ben? Yes.
Would the size of the arrows be like significant how much force there is?
Excellent question. Yes, I'm surprised I haven't talked about that already, right? In fact, when I get to this one, I'll explain that. Okay? The question, her question is the size of the arrow significant? The answer is yes, Howard. Another force that may act on an object could be any physical push or pull, and I usually just call that applied force, or FA. This could be caused by a person pushing a crate on the floor. F, it just means a force, and then the subscript is the kind of force.
Some of the subscripts.
This can be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, the horse pulling on the carriage. We will label the applied push or pull force with an FA, applied force. I just use FA. Okay? This particular reading uses the word tension. Tension in an object results if the pulling force acts at its end, such as in a rope used to pull a boulder. If we say that our carriage is being pulled by a bar, by the horse at the front end, then we can add this force to our FPD. And there we have it. All the forces acting on our carriage have been labeled in the figure. This is the complete FBD for a problem of a carriage being pulled along a road. Now, to get to the question about does the length of the arrows matter? And the answer is yes. This one is clearly more than that one. These are vectors. The longer the arrow, the greater the force, the greater the size. So is there a net force here?
Yeah.
Absolutely. So that means there is an acceleration, right? The F net is this way. One's bigger than the other one, which means there is an acceleration and it's that way. So if it were at rest, it would be, in fact, it's speeding up. If they're the same length, they're balanced. Exactly. Yeah. So is it important that you make them balance or the same length? Yeah, it is. Now I'm not going to get my ruler out and measure to the nearest micrometer, right? If you're within a millimeter or so and I can eyeball it, yeah, they look the same, good. But the flip side is, if it has to be bigger, you better make it bigger. You can't come to me with a ruler and say, well, Mr. Bennett, this one is 1.5 millimeters longer than that one. Okay? Not good enough. Make it like twice the length. Okay? It's got to be long. Okay, a couple examples. The sled. The child next door wants to take his German Shepherd named Spot for a ride on a sled. He chases Spot, who's running away while dragging his sled behind him. What forces are acting on the sled? Well, there's gravity. Most things happen on Earth. I don't know about your life, but mine happens on Earth. So there is a weight force down. You should draw it in there. Okay? FW, weight force. FW, weight force. Yes. It's a force. What kind is it? It's the weight force. Because the sled is being dragged in the ground, we can take there to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. This is called the normal force, Fn. Would those ones be balanced? Mm-hmm. Generally, they are. Because the sled is in motion and the surface with which it has contact is not frictionless, didn't say anything about frictionless, then there is kinetic friction. We tend to live in a left to right world, so we usually put the object moving to the right, which makes the friction backwards. Now, does that one have to be balanced by Fn or Fw? We really have no idea, right? It could be a lot bigger or a lot smaller, we don't know. The child is pulling on the sled, so there's a pull force, F pull, or there's an applied force. May not be parallel to the ground. Most kids tend to sort of pull, up at an angle kind of thing. So it would likely be something like that.
It's okay. It should be great though, right?
If it's accelerating, then actually what you've got, you would actually have to have that part of it, that horizontal component would have to be bigger than this. For now, let's just worry about getting them in there, right? Make sure that you label them. They got to be labeled. You can't just draw diagrams or arrows. Anyway.
That's acceleration force.
Applied force.
And so that can be.
It could be parallel or it could be at an angle. All right, example number 2. This time we have Dot and Spot. Spot, the German Shepherd, being whacked by his best pal. Dot, I didn't make these up. Dot, the Siamese cat. Dot is pulling Spot across the ice rink, disturbing the neighborhood hockey game. What forces are acting on Spot?
The hockey player hitting the stick.
Gravity, weight force. Normal force. It says that it's on an ice rink. That is physics code for no friction. Yes. Loosely packed snow is code for some friction. Rough surface is code for lots of friction. So frictionless, there is the actual answer key shows this as a tension. I prefer just label it FA. Make it simple. Applied force. FA applied. King Kong's pendulum. While climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging around outside the skyscrapers. When King Kong is swinging from a vine, what forces are acting on him?
Gravity.
Gravity.
It was in the air, so
Is there a normal force, Ben?
no, wait,
Yeah, he's going down on the vine if the vine wants to pull
The
on.
normal force is caused by some surface. Is there a surface here?
No.
No normal force, but there has to be an upwards force, you're right. This time, I might say Ft for tension, or I might just call it applied force, right? It's the applied force up. There's no surface, so there's no friction. You could say, Mr. Bennett, there's got to be some air resistance. I'll accept that. Is that what you're going to say, Connor?
Oh, no.
No.
There's so pretty much in all these examples, there's always going to be a weight force.
Pretty much.
It is-
Yeah. Unless you're in a gravity-free environment. Note that I didn't say space. Okay? So, would those be balanced now then, actually?
Yeah.
They'd have to be, right? Because if they weren't balanced, then he'd either be
falling or.
falling or going up.
Makes sense.
No. So they're balanced. In fact, if it was me instead of King Kong, how much tension would there be in the vine?
Less.
I need a number.
70, no, what was the number? 70.
750 newtons, right? I weigh 750 newtons, so there would have to be 750 newtons of force in the vine or the rope or whatever it was. Alrighty, this time our furry friend King Kong has had enough of monkeying around. Thank you. And has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building. Only this time he has taken the elevator. While he's riding up to the top of the building at a constant speed, what forces are acting on him?
Weight.
Gravity.
Upward force with the surface.
Now, there is an upward force.
Wait,
Now, he's riding the elevator at a constant speed.
So there's no acceleration.
No acceleration, so this has to be balanced, and it's the normal force. If it was me riding in the elevator, the normal force would be
Less.
750 newtons. Now, what about when I just get on the elevator? Like it's at rest, right? There has to be a little bit of force to get me going. So at the start, it wouldn't be 750 newtons. It might be
No.
maybe 800 or 850 or something, right? You need something to accelerate me. And once you get moving, and I'm going to give you a chance right away, Connor. Okay? Are there any other forces going on here? Shouldn't be. Okay. Is that the last one?
Yeah.
All right. So what I'm going to do here, you've got about 20 minutes or so. I'm going to give you 11 free body diagrams for you to draw. Okay.
Okay.